Hey everyone, and welcome. Today we're going to break down a really powerful tool in data analysis called simple linear regression. It's a fantastic way to cut through all the random noise and find the clear patterns that might be hiding right in front of you.
You know, at its core, what we're talking about today really answers a pretty basic question. If you know one thing, like, say, how much a company is spending, can you use that to make a really good guess about something else, like how profitable it is? Let's dive in.
Okay, so let's get our hands dirty with some data. Here we've got some numbers for 6 different companies. We have their capital expenditures, that's just what they spend, and their return on assets, which is a measure of their profit. Right now, it's just a table of numbers. Can you see a clear pattern? It's kind of tough, right?
Yeah, just staring at a list of numbers is not the best way to find a story. To really see what's going on, we've got to make this visual. And that brings us to the first big idea, finding something called the line of best fit.
So, what we do is take those numbers and throw them onto a graph. Spending on the bottom axis, profitability going up the side. And, just like that, the mess starts to make sense. You can actually see a pattern starting to emerge from the noise. It looks like as spending goes up, profitability tends to go up too.
And here's the really cool part. Our brains are amazing at this stuff. Without even thinking about it, I bet you can already imagine a single straight line that kind of slices right through the middle of those dots, showing the general direction. That gut feeling, that line you just drew in your head, that is the absolute core of what we're talking about. And that intuitive line you just imagined actually has a formal name, simple linear regression. It's a statistical method that lets us study these kinds of relationships. But it's not about just drawing any old line, it's about finding the one specific line that best represents the data.
So, how do we get from that gut feeling to something precise, something mathematical? Well, we need to translate that line into the language of math. And for that, we need a regression equation.
Now, don't let this equation intimidate you. It looks a little complicated, but it's really just the official recipe for a straight line. The y is what we're trying to predict, in our case, the profitability, and the x is the piece of info we already have, the company spending. Everything else in here just tells us exactly how to draw the perfect line that connects the two.
Let's break down the two most important parts here. First, you have the intercept. Think of that as your starting point. It answers the question, if a company spent absolutely nothing, what would we predict its profitability to be? Then you have the slope. Now, this is where the real story is. The slope tells us exactly how much we expect profitability to go up for every single percentage point increase in spending. It basically tells us the strength and direction of the relationship.
But hang on a second. If you think about it, you could draw a ton of different lines through those data points. I mean, an infinite number of them. So how in the world do we know we found the one true line of best fit?
The answer is we need a rule. We need a system. The goal is to find that one single line that is, on average, the closest it can possibly be to every single one of those dots. We're trying to find the line with the smallest total error.
And this picture shows that challenge perfectly. The line is our prediction. The actual dots, well, that's reality. And that little vertical gap between each dot and our line, that's an error. Statisticians call it a residual. Our job is to find the one line that makes all those little error lines, when you add them all up, as small as possible.
The way we do this is with a really clever technique called the method of least squares. It's a 4-step process. First, you measure that distance, the residual, for every single point. Second, you square each of those distances. Now, why do we do that? Well, it does two really important things. It makes all the errors positive numbers, and it heavily punishes the bigger errors. A point way off the line counts a lot more against you. Third, you add up all those squared numbers. And finally, the line of best fit is the one unique line where that total sum is the absolute smallest it can be. It's literally the line that is the least wrong.
Okay, so now we have this incredibly powerful tool. But just like any power tool, it comes with a safety manual. If you want to be able to trust your results, there are some really important rules of the road you have to follow.
You see, a good regression model is built on a few really key assumptions. You can't just throw it at any old dataset and expect it to work. So we're going to focus on the two biggest ones, the ones you can usually spot just by looking at your graph.
First off, and this might sound ridiculously obvious, but you'd be amazed how often people forget this, the relationship between your variables has to actually be linear. In other words, using a straight line to describe the pattern needs to actually make sense.
For instance, just look at this plot. The data clearly follows a curve, right? It's a U-shape. If you try to force a straight line through that, you can see how badly it fails. It completely misses the actual pattern in the data. you're using the wrong tool for the job.
Okay, the second big rule has a really fancy, kind of scary-sounding name, homoscedasticity. I know, it's a mouthful, but the idea behind it is actually pretty simple. All it means is that the size of your errors, how far the dots are from the line, should be pretty random and consistent all the way along the line. There shouldn't be any kind of obvious pattern to your mistakes.
And here's a classic example of when that rule gets broken. See how the dots start out really close to the line on the left, but then, as you move to the right, they start to fan out and get more and more spread out? This shape is a huge red flag. It's called heteroscedasticity, and it tells you that your model is way less reliable for some data points than for others, and that violates a key assumption.
So, what's the big takeaway here? Simple linear regression is an absolutely fantastic way to find the story hidden in your data. It's powerful, but it is a tool, not a magic wand. Its power is completely dependent on you using it the right way. So you always have to look at your data and check that you're playing by the rules.
Which really just leaves us with one final thought. Now that you understand how to find that single best line to describe a relationship, what hidden patterns, what undiscovered stories are just sitting there in your own data, waiting for you to find them? Thanks so much for joining me.